Hello future engineers, welcome to my YouTube channel. If you're still new to my channel, please don't forget to subscribe and press the notification bell so that you will be updated of my future videos. So this is the continuation of deflection methods 8-in-1. This is part 3.3. So this is the example solution to example 3. And this time, let's solve it by the slope deflection equations and by matrix method. So here we The problem, compute theta A, delta A, theta C just to the left, theta C just to the right, and delta C by the slope deflection equations and by matrix method. IABC is I, then ICF is 1.5 I with modulus of elasticity constant E. So recall the reactions at B, which is 35 upward, then 10 just to the left of C, 372.5 at D, 97.5 at E, then 10 just to the left of C, 10 just to the right of C by action reaction. So we need to have moment BC and moment BA. Moment BC is negative 25 times 2, while moment BA is positive of 50. Negative 25 times 2 is negative 50. So if moment BC is negative, then moment B to A is positive from slope deflection equation, because clockwise moment is positive. So that's why moment BA is clockwise, so it is positive. Then moment at D or moment DE is equal to it is equal to 10 times 6 minus 32 times 6 times 3. So it is moment DE is equal to negative 516 kilonewton meter. So if this moment DC, it is positive 516 kilonewton meter. Moment EF is negative 32 times 1 times 0.5, so negative 16. So let's now set up moment DE. So moment DE equals 2 times E times 1.5I. Remember the equation over L, 8. Then times quantity 2 theta D plus theta E minus 3 times delta E, because the chord joining D and E are support, so the chord will be horizontal, so there will be no delta E, 0 over L. Then minus fixed moment at D, because D is in the left of E, then it is negative 32 L squared over 12. So simplifying this equation, we have 2 theta D plus theta E equals negative 8,288 over 9 EI. Call that equation 1. Then let's set up moment ED. Moment ED is positive 16. So moment EF is negative 16, negative 32 times 1 times 0.5. So moment FE or ED is positive 16 kilonewton meter. So positive 16 equals 2 times 1.5 EI over 8 times theta D plus 2 theta E minus 3 times delta again, which is 0, because we are considering supports that remain unyielding. Then because E is right, so this is E, right? So positive 32 8 square over 12. Simplifying this equation, we have theta D plus 2 theta E equals negative 3712 over 9 EI. Solving equations 1 and 2 simultaneously, we get theta D equals negative 4288 over 9 EI. So because this is negative and the assumption in slope deflection equation clockwise is positive, so therefore this is counterclockwise, or that's the slope at D is positive 4288 over 9 over EI. And theta E is 32 over EI, so that's clockwise, so the actual value of theta is negative. Then we proceed to we consider MCD, which is equal to 0 because this is a hinge, and it is equal to 2 times EI, which is 1.5 I over 6. The length is 6, quantity 2 theta C just to the right, plus theta D, which is already computed, negative 4288 over 9 EI, minus 3 delta C. So let's assume that C rises so that the chord joining C and D is clockwise, so that everything will be positive in slope deflection equation. Then, so minus 3 positive delta C over 6. Again, the assumption is the deflection is upward. Then quantity minus moment at C due to this fixed moment at C is negative 32 6 squared over 12. So simplifying, MCD equals 0 equal to 2 theta C plus, so it's the same equation. Then let's just simplify that. So 2 theta C just to the right minus 0.5 of delta C equals 16 over 9. Then solve it. We also have MDC. MDC is 516. So 516 equals 2E times 1.5 I over 6 times theta C plus 2 times theta D. This is theta D minus 3 times delta C over 6. Then plus, because D is right, positive 32 6 squared over 12. So simplifying this equation, we have theta C plus minus 0.5 of delta C equals positive 16136 over 9 EI. Solving equations 3 and 4 simultaneously, we get theta C just to the right equals negative 10,120 over 9, which is counterclockwise supposedly. So theta C, the slope at theta C just to the right is positive with respect to the sign convention of universal sign convention, which is positive counterclockwise, because this is counterclockwise, so that should be positive. And delta C is negative 17504 over 3 AI. So that means our assumption that delta C is above of D is wrong. So our final answer then is theta C is equal to positive 10,120 over 9 over EI, or in decimal that is equal to 1124.444 over EI, and delta C, because our assumption is wrong that C is above D, so it should be below. And below, or movement of C which is downward, is negative, so negative displacement, and express that in decimal, that's negative 5834.667 over EI. Then we proceed to BC. Moment BC is negative 50, while moment BA is positive 50. So MBC is negative 50 equals 2 times EI over 5. I this time is 1, or EI. Then 2 theta B plus theta C minus, so because C is really going down, so the position of C relative to B is, it is below. So the rotation of the chord is clockwise, and that's also clockwise. So that's treated positive in slope deflection equation. So minus 3 times positive, because that's positive direction. So the rotation is clockwise. So 3 times 17,504 over TI divided by L, which is 5. Then because there's no load in between B and C, so the fixed moment is 0. So simplifying that equation, 2 theta B plus theta C just to the left equals 3375.8 over EI, equation 5. And likewise, MCB, moment at C is 0, is equal to 2 times EI over 5, quantity theta B plus 2 times theta C to the left, minus 3 times delta over L, delta C over L. So delta C is positive because it is going down clockwise, over 5, plus fixed moment is again 0 because there is no load in between B and C. Simplifying, theta B plus 2 theta C just theta B plus 2 theta C just to the left equals 3500.8 over EI. Solving these equations 5 and 6 simultaneously, we get, so let's copy the equations again. So solving these two equations simultaneously, we get theta B equals 1083.6 over EI, and that's clockwise, or if that is required, then that's negative as final answer. Then theta C just to the left is 1208.6 over EI. This is clockwise, so therefore our answer for theta C left is negative 1208.6 over EI because it is clockwise. Then let's have MBA and MBA. MAB. MAB is 0. There's no moment here. Then it is equal to, because there is moment at the far end, it is 2 EI over 2 times quantity 2 theta A plus theta B, which is 1083.6 over EI clockwise from slope deflection equation. Then let's assume that delta A is above, or A is above, so that the rotation of the chord joining AB is clockwise again. So that delta A is treated positive, so minus 3 times delta A over L2. Because there's no load in between A and B, it acts at the end. So imagine that A and B are fixed ends, so that's why there's no fixed moment. So that, simplifying, 2 theta A minus 1.5 of delta A equals negative 1083.6 over EI. Equation 7. Then MBA. MBA is positive 50, and it is equal to 2 times EI over 2 quantity theta A plus 2 theta B, which is this, then minus 3 delta A over 2. There's no load in between, so plus 0. So simplifying, theta A minus 1.5 delta A equals negative 2117.2 over EI, equation 7. So before we solve this, actually, because the far end A for MBA has 0 moment, then we use the alternate equation, supposedly, which is 3 EI over L, times quantity theta near, which is theta B, minus delta over L, or delta A over 2, then minus fixed moment at B, which is 0, minus 1/2 fixed moment at A at the far end, which is also 0. So therefore, we can use that to solve for delta A directly. So 50 equals 3 EI over L2 times theta B minus delta A over 2, or P, or rotation of the chord, which is delta A over 2, then plus fixed moment at B0 minus 1/2 fixed moment at A0. So from here, we can solve delta A directly. And delta A is equal to positive 2100.533 over EI. So that means our assumption that A is above B is correct. So that's why that's the final answer for delta A. Or if we solve equations 7 and 8 simultaneously, then we'll have delta A, theta A equals 1033.6 over EI, because that's positive, that's clockwise by slope deflection equation. And delta A is equal to 31508 over 15, or in decimal, that's the same as this. So theta A is, because this is clockwise, that's negative slope in the universal agreement or convention. So negative 1033.6 over EI, and delta A is positive 2100.533 over EI. So that's it. That's the solution to this problem by slope deflection equation. Method is by matrix method. So the reactions are already shown. Then let's compute MDC as if this is an overhang, because the moment at C is 0. So it is equal to 32. So we have MDE also, and ME. And this is 16. And MED is W32 8 squared over 12. So MDC is equal to 32 times 6 times 3 minus 10 times 6. So MDC is equal to 516 kilonewton meter. So that's why it's already presented here. Then MDE is equal to MEB, and it is equal to 32 W L square over 8. So 32 8 square over 12. Sorry. Then 512 over 3 kilonewton meter. So if this is node 4 and node 5, then at node 4, the loading here should be MDC, which is 516 minus MDE 512 over 3. If it is positive, then it should be applied counterclockwise. So it is positive, it is 516 minus 512 over 3. So we treat clockwise positive minus the counterclockwise, because remember the nodal load is opposite to the net moment at a joint. So because it is positive, so it should be applied counterclockwise. So 1036 over 3. Then the load at E at node 5 would be 512 over 3 minus 16. 512 over 3 minus 16 is positive, so it is also counterclockwise. So let's consider DE. The stiffness of DE is 12 EI over L cube, the first. So because D and E are supports, then we ignore the nodal vertical forces, so F7 only. Then the nodal load at 8 is 1036 over 3. At 9 downward is ignored because we are just concerned of the deflection. So at 10 is 464 over 3. Then we factor out EI. 9 over 256 is from the stiffness of beam element. 12 times 1.5, because I is 1.5, divided by L cube, 8 cube, you'll get 9 over 256. The second one is 6 EI over L square. So 6 times 1.5 over 8 square is 9 over 64. Then this is the negative of this entry here. Then you just copy the 9 over 64 there. Then this is same, 6 EI over L square, so that's 9 over 64. 4 EI, 4 times 1.5 divided by 8 is 0.75. Then this is just the negative of this value here. Then this is half of that value. Then the third row elements are the negatives of the first row elements. And the fourth row elements would be, you copy the second row elements, except that we interchange value 0.75 and 0.375 in this manner, right? And the rest will be copied. Then we have delta D, which is 0, then theta D, then delta E, which is 0 also, then theta E. So we expand rows 2 and 4. So we have, or we expand, we simplify this equation because the other displacements are 0. So that would be 0.75 of theta D plus 0.375 of theta E equals 1036 over 3. Then the other equation is 0.375 of theta D plus 0.75 of theta E equals 464 over 3. So solving these two equations simultaneously, we get theta D equals 4288 over 9 EI, and theta E is equal to negative 32 over EI. So these are the correct signs convention. So it means this is counterclockwise and this is clockwise rotation. So having found that, we proceed to we consider CD because we have found theta D. So remember, we have 10 kilonewton here. So imagine CD to be fixed-ended. Let's solve for the fixed-end forces. So by symmetry, this is 32 times 6 over 2, so 96 upward at C. Then the fixed-end moment here is 32 6 square over 12. 32 times 6 square over 12 is also 96. So that is 96 also. Because there is already an upward load here, so we have 96 for the load, vertical load 96. Supposedly the nodal force is 96 downward, but because there is an upward force here, so the net nodal vertical load at C would be 86 downward. And because this is counterclockwise, so we have clockwise at node 3. So if this is 3, we have 86 downward and 96 clockwise or negative. So F5 is negative, or F5 is negative 86, then F6 is negative 96. So F5 negative 86, F6, F7, then F8 unknowns. Then you just call that F7, F8. EI, then we have 12 times 1.5 over 6 cubed is 1 over 12. Then this is 6 times 1.5 over 6 square is 1/4. Then copy this element here, this cell here, then copy this here. But this one is negative of that value. Then this is 6 times 1.5 over 6 square, so 1/4. This is 4 times 1.5 divided by 6, so 1. Then the negative of this first item. Then half of 1 is 0.5. Then the negatives of the first row. Then we copy the second row, except we interchange these two values position. So then we have delta C unknown here, delta C, theta C just to the right, then 0 because there's no displacement at B, and theta D is 4288 over 9 EI, which we have just computed from here. So we expand the first two rows, so negative 86, negative 96. Then we have EI times quantity 1 over 12, 1/4, 1/4, 1, then delta C, theta C just to the right, plus EI times quantity negative 112, 1/4, negative 1/4.5 of quantity 0, 4288 over 9 EI. So simplifying or expanding this part, so negative 112 over times 0 is 0. 1/4 of 4288 over 9 is, that's positive. So therefore, the new entry here is negative 86 minus 1/4 of 4288 over 9. So that would be negative 1846 over 9. Then this one is negative 96. So 0. So this is positive. So negative 96 minus 0.5 of 4288 over 9 is negative 3008 over 9. Then we have EI. Copy this entry. And we have 1/12 delta C plus 1/4 theta C plus equals negative 1846 over 9. Then 1/4 delta C plus theta C just to the right equals negative 3008 over 9. Solving these two equations simultaneously, we get delta C equals negative 5834.667 over EI, and theta C just to the right is equal to positive 1124.44 over EI, just like before. Then we consider BC. So this is BC. Then remember, we have a load here 10. There's no load in between. Then the moment here at B just to the left is 50. 25 times 2 is 50, and it should be clockwise so that it opposes the moment due to the 25 kilonewton load. So if this is B, then the nodal forces at B would be F3, and F4 is equal to the opposite of clockwise moment is counterclockwise 50. So we have counterclockwise 50, and because this is B, the displacement is vertical deflection is 0, so we'll just don't mind that. Then at 3, we have 10 kilonewton downward only. So let's set up F3, then we have 50, then negative 10, then don't mind, you just call it F6, EI, then 12 times 1, because EI is constant here, divided by 5 cube is 12 over 125. This is 6 times 1 over 5 square, so 6 over 25. The negative of this first entry, then we copy that 6 over 25 there. Then this is 6 EI over L square, so 6 over 25. This is 4 times 1 over 5, so 4 over 5 is 0.8. then the negative of 6 over 25, then 1/2 of 0.8 is 0.4, the negative of the first row, again, then copy the second row, except that we interchange the second and the fourth position, like that. And we have 0 displacement at B, then we want rotation at B, theta B, then we have already computed the delta C, which is negative 17,504 over T in decimal, equivalent to this, then theta C just to the left. So we expand rows 2 and 3. So let's expand rows 2 and 3. This is the matrix before. So we have negative 50, negative 10 equals EI 0.8, negative rows 2 and 4 rather. So this is rows 2 and 3. Rows 2 and 3, sorry. So 0.8, 0.4, negative 6 over 25, negative 6 over 25. And we have quantity theta B and theta C just to the left. Then plus EI of 6 over 25, negative 6 over 25, 6 over 25, negative 6 over 25 times 0 and negative 17,504 over 2EI. So this new entry value here is equal to 50, and we have 0, this is positive, so 50 minus 6 over 25 times 17,504 over 3, that would be negative 33758 over 25, then negative 10 plus, because 12 times 1 over 12 over 125 times negative 17,504 over 2 is negative. When we transpose it, then it becomes positive. So negative 10 plus 12 over 125 times 17,504 over 3 is 68766 over 125. Then we have EI, we just copy this, 0.8, 0.4, negative 6 over 25, negative 6 over 25. Then we'll have here delta C, theta B and theta C just to the left. So solving for theta B, it is negative 1083.6 over EI, and theta C just to the left is equal to negative 1208.6 over EI. Then let's consider AB, the last. So the load at 1 is, because we don't mind B because we have found theta B, so it's just the load which is 25 downward and there's no moment. So F1 is negative 25, F2 is 0, F3 don't mind, F4 don't mind, then EI. Then 12 times 1 over 2 cube is 1.5. 6 times 1 over 2 square is 1.5. Then the negative of the first. Then you just copy that. Then this is 6 times 1 over 2 square, so 1.5. 4 times 1 over 2 is 2. 4 times 1 over 2 is 2. Then the negative of the first entry. Then 1/2 of the second entry here. Then the negative of the first row. Then this is the second row, except that we interchange position between the second and the fourth. Then we have delta A, theta A as the unknowns, and 0 displacement, then negative 1083.6 over EI, which is equal to theta B. This is delta B, so 0. So expanding rows 1 and 2, so negative 25, 0 equals EI matrix 1.5, 1.5, 1.52 times delta A, theta A, plus another matrix EI times negative 1.5, 1.5, negative 1.51 times the matrix 0 and negative 1083.6 over EI. So the new value here is negative 25, then 0, 1.5 times negative, so positive. So this is negative 25 plus 1.5 times 1083.6. And the second entry is 0. So negative 1.500, then negative 1083.6 times 1 is negative 1083.6 over EI times EI, so cancel. So 0 plus 1083.6 is 1083.6. So negative 25, then my plus 1.5 times 83.6 is 1600.4. Then 0 plus 1 times 0 plus 1083.6 is 1083.6. Then solving these equations, 1.5 delta A plus 1.5 theta A equals 1600.4. Then the second equation, 1.5 delta A plus 2 delta theta A is equal to 1083.6. So solving the two equations simultaneously, we get delta A equals 2100.533 over EI, and theta A is equal to negative 1033.6 over EI. So that's it. And these answers are similar to the other methods, 7 methods of solving computing deflections. So I hope that you are able to follow the solution, though this problem is challenging, a little bit challenging.